Nested learning, the illusion of deep learning architecture, argues that raw depth isn't the secret sauce. The authors propose seeing a model as a stack of learning processes nested inside each other, multiple optimization loops, each with its own context, influencing one another. This shift moves us from a network trained by an optimizer to a system of learners that learn how to learn. In that lens, in-context learning becomes a byproduct of how a model compresses and uses its recent context. It also opens the door to models that can modify their own learning rules and manage memory across timescales, aiming for higher-order in-context learning and true continual learning. Big picture. Reorganize learning itself, not just add layers. Core idea. Treat a learning system as nested optimization problems with their own context flowing between levels. Instead of one flat training loop, you have multiple, possibly parallel loops that read, compress, and update context. From this view, in-context learning isn't mysterious. It's the model compressing recent information into working state and reusing it like a clever scratch pad. 3 contributions follow. First, optimizers like SGD with momentum or Atom are reframed as associative memory modules that compress gradient history. That perspective lets you design more expressive, deep memory optimizers, not just tune learning rates. Second, a self-modifying sequence model that learns its own update rules, so the model can adapt how it learns, not only what it predicts. Third, a continuum memory system that replaces the rigid short-term/long-term split with smoothly varying timescales. Combine the self-modifying learner with continuum memory and you get HOPE, a continual learning module showing promising results in language modeling, knowledge integration, few-shot generalization, and long context reasoning. The bet: more levels of learning yield higher order in-context learning and durable on-the-fly improvement. Quick backdrop. Classic ML learn from data via gradient-based optimization and deep learning automated feature discovery, unlocking huge wins across vision, language, biology, and games. But those successes mostly target fixed tasks and static training. The paper is motivating a different goal: systems that learn within context, modify how they learn, and keep improving over time, without retraining from scratch. Stacking layers boosts representational capacity and flops. Great for static, in-distribution prediction, but it doesn't automatically increase a model's computational depth in the algorithmic sense. Think of it like adding more gears without adding loops. You can process more in parallel, yet struggle to run multi-step procedures that require iterative control flow or memory management. That's why some tasks demand explicit mechanisms for reasoning over steps, not just wider feature extractors. Also, simply scaling width/depth can hit diminishing returns for certain parameter classes. Some capabilities don't grow meaningfully just by piling on more neurons. Finally, optimization matters. A deep model with a mismatched or shallow optimizer can converge to suboptimal solutions. The takeaway: depth alone is a blunt instrument. If we want models that adapt on the fly, reason over longer horizons, and avoid training traps, we need to redesign the learning process itself: how memory is stored, how updates are computed, and how multiple learning loops interact.